What is the electron correlation problem in molecular simulation? Imagine trying to predict how a crowded dance floor moves when everyone is constantly shifting and avoiding each other. Now, picture doing that with electrons inside a molecule. That's essentially what the electron correlation problem is about. It's a big challenge in understanding molecules because electrons don't just move independently. They influence each other's paths in very complex ways. In simple models, like the Hartree-Fock method, electrons are treated as if they are moving alone in an average field created by all the others. But this ignores the real-time interactions, or correlations, between electrons. This leads to errors because electrons repel each other due to their negative charges, and they also follow quantum rules that make their behavior even more intertwined. There are two main types of electron correlation. The first is Fermi correlation, which comes from the Pauli exclusion principle. This principle says electrons with the same spin cannot occupy the same space, so they spread out. The second is Coulomb correlation, which is about how electrons dynamically avoid each other because of their electrostatic repulsion. Both types are important for accurate predictions. The problem is that modeling these interactions exactly is very difficult. It's a many-body problem, meaning all electrons influence each other at once. Classical computers struggle with this because the calculations grow exponentially more complex as molecules get bigger. That's why methods like configuration interaction, coupled cluster, and quantum Monte Carlo are used. They try to include electron correlation but come with high computational costs. This is where emerging quantum technologies come into play. Quantum computers and quantum simulators can naturally encode the complex quantum states of electrons, making it easier to simulate electron correlation accurately. They can handle strongly correlated systems that classical computers find nearly impossible to model precisely. In practical terms, simulating electron correlation helps us predict how molecules behave, how reactions happen, and what properties materials might have. Quantum molecular dynamics simulations can incorporate these effects to give more reliable results. Hybrid quantum classical methods combine the best of both worlds by using quantum computers to handle the electronically correlated part of a system while classical computers manage the rest. Quantum Monte Carlo techniques also aim to solve the electron correlation problem more exactly, though they requiring significant computational resources. To sum up, the electron correlation problem is about capturing how electrons influence each other's movements in molecules. Overcoming this challenge is key to making more precise molecular models. As quantum technologies develop, they promise to revolutionize how we understand and predict molecular behavior, opening new doors in chemistry, materials science, and beyond.